Alrighty, welcome to day 12. Day 12 is the last day of Advent of Code this year. I do have to say that after looking through how everybody else solved day 10 part 2, that I submitted to Z3 and actually just let the solver solve the problem. It doesn't seem like there's really another solution. One of them popped up out of all of the answers. One of them popped up over the last, say, like 10 hours or so. So I might go back and take a look at that. But 99.99% of people did Z3, which I don't love. So day 12, Christmas tree farm. We're almost out of time. Presents, our input looks like this. It is a list of present shapes. Okay. List of present shapes and size of the region under each tree, and a list of each shape that needs to fit. So this 4x4 section needs to fit, I think, 2 of these presents. And this 12x5 would have a first entry, a third entry, and 1 of each of the fourth and fifth. The first section lists all the shapes. Second section lists the regions. Presents can be flipped and rotated. How many of the regions can fit the presents listed? So we've got a 4x4 region, and we need to figure out if we can fit 2 shape 4 presents in it. The third region is impossible to fit the presents into. So 2 regions can fit all their listed presents. How many of the regions can fit all of the presents listed? Okay, I don't know about this. Let's take a look at the puzzle input just to see what we're working with here. Oh, there's a lot of presents. So 21, 29. You can call this like 120 presents and assume that the ones down here are pretty similar. A couple of them are even more. 1, 2, 300 and something. I don't know the algorithm for this one, which feels really unfortunate. I don't know. It feels somewhat like there's some kind of Tetris vibe here. Kind of going to start searching for like some kind of algorithm for fitting shapes into a space of some kind. And I've kind of immediately come up with packing problems and knapsack problems. Then there's the bin packing problems. When the number of bins is restricted to 1 and each item is characterized by both a volume and a value. The problem of maximizing the value of items is known as the knapsack problem. Okay, so knapsack is a specialization of bin packing. We don't have a 0 to 1 because we have multiple items for each bin. Unbounded knapsack places no restrictions on copies, and it would be a dynamic programming potential solution. I don't immediately see how testing the permutations of 300 elements positions in a grid is going to be helped by caching. I guess in some sense there is a bunch of similar configurations, and maybe there's enough similar subset configurations for the caching to help. The only problem is that this is 10 different items with weight limits, and we have 10 different items needing to like put them into specific positions. There's circle packing has a whole section, cubish things, spheres. These are all like identical shapes, as well as kind of arbitrary positioning. Like we can't rotate 45 degrees. So even given a space like this yellow and green cube, we will never be able to rotate this. Part 1 is just decidability-ish, right? Like the 2 can fit all of their listed presents. So we only need to find one solution, but we need to know if we can't find a solution. I don't know much about like optimal packing subsets, so I don't know how these would optimally combine to be, I guess, like irreducible. Packing of regular objects is not a problem lending itself to closed form solutions. I'm going to try searching for something that's a little bit more like Tetris packing problem. Tetris is totally discrete. We can represent the Tetris game as a graph with 200 nodes. Interesting. When viewed the board like this, you think this is reasonably close to the class of graph covering problem. Interesting. I doubt that there's anything that fits exactly here, but I guess it's worth taking a look at what kind of algorithms we have inside of things like PetGraph. I think that because all of these descriptions of bin packing and knapsack and packing and covering that I'm looking at, they all use like similarly shaped blocks. So maybe we give this a whirl with a simplified version where we end up with basically like just the 3x3. So we've got what, 1, 2, 3, 4, 5, 6 presents here. So we've got 6 3x3s. And if we've got 12 by 5, that's 60. And there is 1, 2, 3, 4, 5, 6 to fit. And 9 times 6 is 54. So we're saying that the math works out such that if we just treat these as blocks, then this one fits and this one doesn't. And we're only trying to figure out if they could theoretically fit. Is our puzzle input is all 3x3 blocks, 1, 2, 3, 4, 5, 6 3x3 blocks. I guess theoretically another step could be like, do any of these fit into each other? But none of them seem to. None of them are small enough to actually fit together and make one block. So I think this is a trick. I think there's a lot of description here for something that is potentially not needing that description. So let's roll with that to start with and see if it works. Because I think if we end up with something that is not that, we potentially have an issue. Like an actual, like, is this even solvable kind of issue? So these are all 3x3 and we actually don't even need to parse them. Right? Like if we're going to take this approach, these are all 3x3. All of the input is also 3x3. So we really just need to count the number of them, but I think the number is the same, right? There's still 5. So why don't I do this? We'll do let present count equals 5. And this is 5 3x3 presents. I'm kind of debating what I want to return here. I'm not really sure exactly what I'm going to do here. If I'm just going to need to do a like total size check, right? If we're doing, because like 12 times 5 with the math for this, one fits in the other. And then this doesn't fit, right? 5, 6, 7. 7 times 9 is 63. So we do 12 times 5 is 60, and that doesn't fit. So just doing the like very simple math works, which doesn't feel like that much of a puzzle. But we'll do a line ending with a separated pair followed by something and then separated lists. We could fold this, but I still want to kind of keep some of the data. Like, I'm not sure this approach is going to work. So if we were writing this parser to just accumulate these numbers, and I knew that that was the answer, then I could write this with a fold and just accumulate those values now, and then just end up with a parser that returns like total space and desired space or something like that, or total space and like number of presents. But I don't know that that's what we need. So I'm going to do this a little bit more naively. So we're going to do a tag for semicolon here and a space 1. And then I think this gives us everything we need as long as I pull in all my imports. And I'll pull in the non-parser trait here so we have access to the parse function. And this then would be a vec of tuple, u32, u32, vec, u32, right? Because every separated pair is a tuple, every separated list is a vec. So we end up with tuple of u32s, tuple, and then 2 vec. So we end up with, I'm going to be, if this actually works, I'm going to be kind of disappointed, but I think it has to. So we end up with 4, 4, 0, 0, 0, 0, 2, 0, 12, 5, 12, 5, 101, 2, 2, 101, 3, 2. Okay, so we've got all the numbers we need. Then the answer here, theoretically, will be lines.iter.map, and this is going to be xy present, right? So we have xy and the vec of u32s. The vec of u32s, I think, just gets added together. So we can do, I guess we can do filter map here. If x dot y, or x times y, is greater than present sum, I guess it's not present sum, right? It's present sum times present size, which is like 3x3 is like 9, right? So we don't actually need the present count. We need the present size, and the present size is 9. And then we count, and we get the result, and I get some type errors because of references and stuff. This is filter mapping, so technically speaking, we could put all this into... I'm just going to return unit. We're going to dump everything. Okay, I haven't built the test yet. because part 1. Okay, cool. So that at least doesn't work, which is probably good. I guess I could have figured that out earlier. I feel like the actual solution is going to be extremely to even be able to run this, we need to get rid of the input. These are all 3 by 3, right? 3 by 3, 0, 1, 2, 0, 1, 2. So this gives us a number. I'm curious to know if this is bigger or smaller than it's supposed to be. Cool. Just not the right answer at all. Which means that we need to do some additional checking. So let's try one more heuristic here, I think. The present parsing feels like it actually comes into scope. So let me bring that back into the input, and I'll bring that back into the test by grabbing it. So I think that the next step that I want to try is determine if all of the hashes, like the count of the hashes, fits under the number, because I think that's the only way that part 1 works. Or sorry, not part 1. 4 by 4, if we have 2, 9 times 9 is 18, right? But this is 0, 1, 2, 3, 4. This is the 4th present, so it's this one, which is 1, 2, 3, 4, 5, 6, 7, which is 14, which would fit. And then this one, 1, 2, let's see. Let's try to count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 plus 3 and 2, 21 plus 14, 35, 39, 49. That doesn't work in the other direction, right? 12 times 5 is 60. I'm not doing my math wrong, right? Yeah, 60. I suspect, I think that the test, I think it's different. I think the test input is different than the real input. I'm moving forward with that assumption still. So I need to count these numbers then. Or I guess the count isn't really what we're looking for. I feel like there's a way to cut this down, and I'm just not modeling it correctly. Hang on. So what we're doing right now is the size of the grid and checking against the maximum present size, which is 9. So the maximum present size is 3 by 3. If we have 60, this is 16 versus 18. So if we count 3 by 3 positions, this doesn't work. If we count number of spaces, this works. Wait, all of these are size 7. Yeah, so this confirms it. So if we go for just spaces, it's too high. If we go for just 3 by 3 grid size, it's too low. The actual input, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. The actual input doesn't have them all be 7. Let's see what number I get with the, well, we have to parse these counts, I guess, if I'm going to use the lower number. It unfortunately doesn't work on the test input, but I'm not sure if that's a trick or not. This absolutely feels like one of those days where the problem setup is basically impossible, and there's something about the input or something that is just makes it very clear, which feels weird because then I don't know what information I actually need out of this parsing. So I wrote the parser out in an extremely just hacky, straightforward way. I know that a lot of people don't write, or rather, people who are not familiar with NOM will find this very messy. That's okay. I just wanted to hack something out. This is many1, so it's many of the contained parsers. This is terminated, so it's U32 terminated by a colon and a line ending. This is recognize, which is new, which will recognize many of these characters and then allow me to map over the input string. So it recognizes these characters and returns me the full input string for everything that it mapped over, in which case I can just cars filter for hashes and get the count. And then for our full parse, we end up with this extra type here. So we end up with our presence vec in the first and our other vec that we already had in the second. And just to make sure we have the full input down here, because I've been messing with it, it's there. And we end up with 77777, which is the right amount. So theoretically, we tested the, I guess, upper bound is what I would say. So 503 is our upper bound for if everything gets its own spot, basically. That's not entirely true, because just having your own spot, yeah, I guess that makes sense. And I'm going to check basically the lower bound now. The lower bound being if we only account for the number of like items in that particular, so present size here then is presence iter enumerate, I guess, enumerate map, which is index presence and num presence, which should be presence index times num presence sum. So if we run this on part 1, we end up with 0. 0 is wrong. 0? I did my math wrong, didn't I? Why does this work on the test and give me 0 for the actual input? If we enumerate over the presence... Ooh, I renamed these. Hang on. Let me fix this here, I think. Num presence. Let's call this present count, right? Present count. And then we map... so we iterate over the present counts. We map the index to the present in the presence array. We get our num presence. Num presence, I think, is a U32, so we need to do this like as usize, because I think presence index is a usize. Maybe it's not. Maybe I should just run and let the compiler tell me what the issue is. Oh, these are all in order, right? I didn't check. 0, 1, 2, 3, 4, 5. Yeah, they're all in order. So we can just kind of ignore the index in the original and just go directly for that. And this can sum into a usize because we'll have a usize, right? I don't think that we need a usize, so maybe we go the other direction, actually. U32, right? Yada, yada. Value of type U32 cannot be made by summing an iterator of usize, yada, yada. That makes sense. No implementation for usize times U32. So we'll make this a U32, and then make sure that we fix our borrowing issue now that we've fixed our variables. Okay, and this is 531. Did I say this is lower bound and upper bound? I think I have them back mixed up. So I think that's our, oh no. Yeah, okay, so that, yep, I was right. I was right in that it is a trick. So basically we just did a test for the lower bound and upper bound without actually solving the problem, and we end up with the lower bound. I'm named them wrong here, but we have basically lower bound and upper bound. And our upper bound is actually the one that worked for us, which I don't feel good about because I feel like, anyway, doesn't matter how I feel about it. I feel like there's not much to say here. I wrote some messy code because I wasn't really sure if this was even going to be like code that was used in the long term. Probably the most interesting thing here is the parsing, actually. So when we parse, we do a present. So this is a tuple. We do the present parser and then a separated list. This is a vec. Very typical, very much like what we've seen in previous days, so I probably won't cover it. It's a list in pairs and tags and stuff. The present parser is more interesting. We use many1, which means that this whole tuple here is going to get repeatedly applied and then collected into a vec. So the difference between a separated list and many1 is interesting because a separated list requires that you specify the in-between character, and if it doesn't see the in-between character afterwards, then it's done. But for many1, we will just be applying this parser. So if we want to take that new line off the end, we kind of have to handle that ourselves. So in this case, we start off with the first line, which is 0 semicolon, right? And I write this in a very specific way. So it's U32 followed by a terminator, which is the semicolon and line ending. And then we recognize many hashes, dots, and line endings, which basically, if we think about the parsing, we start here and we end here. So this is the string slice that we get out of that recognize. Recognize will allow you to pass in any parser and then return anything that it parsed. Nom these days has this really cool thing where it will switch output modes. So this doesn't actually generate the emit. So it doesn't generate like the parsed value, which is really cool. It just generates basically the check. And then we map over that string slice and we do the cars to find the count. This could probably be a different parser, right? Here's recognize in the docs, but there's also one of. So one of can be a simpler way to write this pattern where it's basically give me a set of characters and it will parse out that character. Now the downside of using one of here would be that line ending actually isn't just a simple character. It's for new lines and carriage returns, but in more cases than not, you'll have something a bit different. It's pretty common to see people try to use take while for this kind of thing. And you could do a take while for a function that checks for if the character is not a number, which would also work. So there's multiple options here. This is just a very like straightforward, very composable way to write it. But it doesn't have to be like this. It can be different. This is also just like writing the parser such that I don't know what I'm going to change it to in the future because I don't know what information we actually want. So I'm writing it in the way that will let me change it the most easily in the future rather than fit the problem the best. So once we have presence in lines, what we're doing here is basically just multiplying the area that we have and testing to see if it matches the available area we need. And that's it, which is kind of a disappointing answer for me for today. I was hoping to like learn a new algorithm or something, but it is what it is. I hope that you all had a great time for this Advent of Code. It's only 12 days, so it's a little bit shorter than last year, but we'll be back again next year. If you found this fun, we always have a recurring participation in the Discord as well, so feel free to join that either for next year or for future Rust conversations. And I hope you had a good time, and I'll see you next year. Actually, I forgot to check the visualization. So if we continue to part 2, I just assumed that we wouldn't have a part 2 because of past years, but we actually don't have a part 2. We literally don't. The number that it judges on is based on the number of stars for 25 days. Always part 2 for the last day is like not a problem. So we have enough stars to finish decorating the North Pole and we get to click. If you didn't have all the stars, this would show some number. 23 is the wrong number. And now we get our little background. And now we can all see the Easter eggs in all the puzzles and stuff like that, which is very cool. So now if you go back to say like day 5, there's a bunch of things here that theoretically are supposed to have spoilers on them, or like whatever, but this one doesn't for some reason. There we go. It's in the title tag, isn't it? Which you can see if you like right click and actually check. So it's span title equals, joke explanation or something like that. So feel free to go through those and check them out if you're interested in that kind of thing. And otherwise, I will see you next year. Have a great rest of your year.